Welcome to the pre-recording of lecture 21 of an introductory course in supercomputing. So this is the next to last lecture in a first sequence on GPU acceleration. So we will consider again our running example of matrix multiplication, but now with a particular care on the device memories. So in the previous lecture we introduced a very basic version of the matrix multiplication. Now we are going to look into a more efficient version, a version that will take care of the memories that are available on the graphics processing unit. In a way, this is a very technical lecture, but on the other hand also very rewarding, as you can see as a programmer the different memories that are available. So most modern programming environments will shield that information from you. Programming, writing very highly performant programs on the GPU actually require that you are aware of the memory architecture. Okay, so let us look into the way data is stored on a graphics card. So we have already covered that there is the memory on the host where everything originates and also where everything ends, and there is the memory on the device. So in every accelerated program we must allocate memory, also deallocate afterwards, and also transfer data from the host to the device, and afterwards doing the transfer of the results from the device to the host. So by default, if we don't really specify much, then the memory on the device is the global memory. The global memory is about very similar to the random access memory on the CPU, on the host. All threads have access to the global memory. In addition to the global memory, we distinguish between local variables, which are local variables for each thread are stored in registers. All threads in one block have access to shared memory. And there is also constant memory that is accessible to all threads in all blocks on a grid, and that is very useful for constants because it's a read-only memory. So during the execution of the kernel, threads can only read from constant memory. So these are the main definitions. Actually, here is the critical definition: the compute to global memory access ratio. So this is the number of floating point calculations performed per each access to the global memory. Earlier in the course we distinguished between memory bound and compute bound, very important in any computation, even if it's not parallel. So if a computation is memory bound, and here if you have a compute to global memory access ratio of 1, then actually you will have a memory bound computation, and then the memory clock rate will determine your performance. So there is still then a lot that you can do. Then it's even more critical that you understand and carefully apply the hierarchies, the global memory, shared memory, registers. Otherwise, you will miss the theoretical peak performance. So in a way, conceptually, the CGMA ratio is the main concept of today. Here is a picture. We have threads that are launched in a block of grids. So here the blocks are two-dimensional. So in the next lecture we will see more about thread hierarchies. We have the registers, for purposes of spacing, so there are only two threads in each block. So every thread has its own registers, its own local variables as a programmer. Every thread can read and write directly into shared memory. So the shared memory is the memory available for all threads within a block. And each thread can also read and write directly into global memory. Each thread can read from the constant memory. So then there is the little block at the bottom left, so that's the host. So before and after execution, there are the transfers to the data. So the host can put all the data first in the global memory, and the results are then also retrieved from global memory. The host can also set the constants in the constant memory. Typically, there is also a sequential hierarchy. So threads will first read from global memory into shared memory, from shared memory into registers. This will lead to more instructions and will actually more fully occupy the GPU, while one thread is waiting for its data, while one block of threads is waiting for data, another instruction by another block of threads can be executed if you have these layered memory accesses. Okay, so what do we have? So here is again the fastest memory, actually, the registers. So registers, they can be identified with local variables in a function. So you use registers typically to have the results that you are computing. So we had the inner product in the matrix multiplication that is frequently updated. So in every step of the process of the computation, and that is better stored in a register, because registers are very quick to access and update. The evolution of the 32-bit registers. So the first graphics card was on an Intel MacBook. It was a graphics card the graphics card was from NVIDIA, so I was able to run it there. So you see the number of threads that are available per block. 65,000 may look like a whole lot, but observe that it has not changed Kepler, Pascal, Volta, so they actually all have the same number of registers. We will in the next lecture see that if you are using too many registers, that could lead to a very steep loss of performance. And in other cases, as I have experienced, it may actually even also lead to a loss of accuracy in the results. Some things work better on newer graphics cards. Nevertheless, it's still massively parallelism, so we will launch many more threads of one magnitude more than we have available cores. Then the shared memory. So the shared memory is faster than accessing to global memory, not as fast as registers. So here the virtue is that when you process data, and we do this in a data parallel manner, so we work on one array of numbers stored sequentially, and all threads in a block read adjacent locations in main memory. So the benefit of the shared memory is that this can be done in a highly parallel manner. The reading of the data from shared memory into the registers, or also from the registers the writing onto the shared memory, and then from there on onto the global memory. A typical characteristic for graphics cards were the small memories. So the bottom line of the slide is again that the amount of shared memory has not increased in the three Kepler, Pascal, and Volta graphics cards. And as an exercise, you're welcome to check what it is for Ampere and Hopper. Then comes the global memory, and the story continues. So look at the bottom line here. The global memory, which is similar to the random access memory on the CPU, but these days 16 gigabytes and 32 gigabytes are actually common on any, perhaps even any laptop or an ordinary computer. Pascal, the workstation where the GPU is hosted, has 256 gigabytes of internal memory. So you see that memory here is we are still very pressed in memory, but you see that in the evolution of the graphics card, so starting from the Tesla Kepler, the Tesla C2050, then the Kepler, the Pascal, and the Volta, you see that the memory actually doubled. And that's a very good thing, also most likely necessary for the applications. Otherwise, you are forced to read and write to the random access memory of the CPU again. And that is even a slower movement. The cache has also increased. Constant memory has actually stayed constant for the earliest NVIDIA graphics card that I was using in a laptop, up to the Volta, the most recent graphics cards that I'm using. So all this information can be obtained from the device query in the software development kit of NVIDIA. Okay, so here is a summary. I copied this from the white paper on Kepler. So we have three different memories, the registers per thread, then the shared memory per block, and then per grid the global memory. Okay, so how do we use these memories as programmers? We have to be aware of the scope and the lifetime of each memory, each storage that we access through variables. The scope are the threads that can access the variables. So again, a register is one thread, shared memory one block of threads, global memory the all the threads. So it's a very important for synchronization. You should avoid at all costs that data parallelism can only happen if you have data independence. So avoid that threads write in the same or read from the same location in shared memory, the same for global memory. You can also often not count on the fact that when different blocks of threads are executed within the same grid even, you don't really have control on where every thread writes into global memory at what time. So the lifetime, so the registers, they only live as long as the threads are executed. Again, it's a little bit confusing because all threads within the grid execute the same code. And you have only one variable name that you see, but that variable name is duplicated among all the threads in the grid, and that is thousands of variables there. So at that moment, it's actually very difficult to see the lifetime. So the lifetime of every variable is only actually alive when the thread is executed. And actually it's even more complicated when that particular instruction in the code is executed. Okay, so this is important. So if you launch, so lifetime is important because you cannot always assume that the initial value for a variable is always 0. It may be if you launch a thread, if you launch a kernel only once, but if you then launch it again and you forgot to initialize, then you may see unexpected results. Also, when you assign, you have to be careful that if you want the storage to persist, you have to write into global memory. You cannot count that shared memory persist after the execution of the threads of the kernel has ended. Okay, scope and lifetime, important concepts. So as a programmer, you make the difference between atomic variables and array variables. In general, as programmers, we have elementary data types and composite data types. It's important that only atomic variables can ever get into a register. So you will never get an entire array into registers. That should be clear. So that's just the main difference already between array variables and elementary data types like numbers. You, as a programmer, you have these keywords. If you don't specify any keyword, then it may end up in the global memory. So you have to, if you want something in shared memory, then you have to explicitly use the shared keyword. Also, if you are declaring constants, you have to use that keyword in front of it. Again, if you haven't not been doing this that much, and often in a program you would declare a constant all the way on top, and then if the constant is global, then any function that is defined later has access to this constant if you have a normal sequential program. This is not the case with GPU programming. You have to put it explicitly in the constant memory, explicitly declare it that will be used into a constant. So it's important to make the distinction also for the scope. So you see local arrays. So inside one function, one kernel function, you can work with a local array. Most likely you're going to put it into the shared memory, because you could in principle have a local variable that is an array, and then only the thread sees it. So this is where the shared is extremely important. So if you forget the shared, then it may be considered as a local variable. Global variables, you often have them, or you have them as the arguments in the function, in the kernel function. And then they are global for the entire duration, for the entire lifetime of the program. Okay, so let us now illustrate this with our running application, so the matrix multiplication. So before we had a very simple C application, C implementation, so where we were computing the inner products via this statement in a loop. So this was data parallelism, so the ith thread executed this statement and wrote it and updated each time in the ith memory location in the linear addressing space for the arrays. I kind of indicated that this was not a good idea to do, but at the time we were thinking about mostly logical correctness. That always comes first. Okay, so pointer arithmetic. So we update the pointers after we have used them. So if you count the operations, we do one floating point addition, so the plus equals, and we do one multiplication. Or actually said differently, we first do the floating point multiplication and then we do the update with the plus. So typically in the compute to global memory access, we only count the floating point operations. So the operations that are involved in the update of the indices, both so in both in the A and the B matrices, we actually don't really count this. But see now, the compute to global memory access ratio of 1 was already pretty bad, but here actually we have less than 1, because we do 3 memory accesses. We are doing a memory access in A, reading from an element from the matrix A, reading an element from the matrix B, and then writing into C. So we do 3 global memory accesses for 2 floating point operations. Nevertheless, last time we got good performance because of the excellent peak memory bandwidth in the graphics cards. But still, this is not very good. And by now, with the insights that we have in the memory hierarchies, so instead of global memory, we better read into shared memory. And then as we are computing this inner product, we better store everything in registers. Okay, but here is a better idea. Tiling tiling means it's more or less a divide and conquer strategy. When we discussed tasking, we had a first blocked way of computing a matrix product with blocks of matrices. In blocks are typically mapped to tiles, so this is data parallelism. We have a tile which will correspond to the memory in shared memory, and we have the block of threads that is currently considering the tiles that are computed. So we are going to subdivide our matrices into tiles of width W. So typically we now see the matrix multiplication as the multiplication of many smaller matrices. It introduces a lot more instructions, which is also very favorable for having a lot more parallelism, while one block of threads is doing the arithmetical operation, another block of threads can work on the memory movements. Here is the picture. So instead of having now one row of A, one column of B, we consider blocks. So the central block in the matrix C involves two blocks of A and two blocks of B. So this is still, for the sake of the picture, a very coarse subdivision of the work here. But you kind of get the idea of tiling, I hope. All right, and this is how it's actually done in the software that comes within the software development kit. So we are following the hands-on textbook from Kirk and Hoog, which is in turn based on the CUDA programming guide. So let's run this. I've run this, so I've taught this course already now more than 10 years. So the computers are still all around, so I can still verify this. I have not updated the materials for Volta, but I hope that it becomes clear. So let's look at the software development kit, which is actually using the CUDA BLAS. So this is the first run is done with Compute 1.1 capability. This card did not have the capability yet of did not have the double precision compute capability. So it's important to keep in mind that everything is done with 32-bit floats, single floating point precision. Nevertheless, on this card in a graphics in a simple laptop, you see that we get 5 gigaflops as the performance. So there is the CUDA BLAS and the CUDA matrix multiplication. So the CUDA BLAS is actually the winner, and that has been also the general story here. If you ever have to use matrix multiplication, use the most optimized CUDA BLAS. Now the processors work at gigahertz, so even in this simple laptop you actually get a really great performance, and you might actually not achieve this if you would compare this to the host. Then the C2050, that was the first high-end compute graphics card. So you see the compute capability is 2.0. And then you see we have really great performance. So the CUDA blast get 400 gigaflops. The matrix multiplication from the software development kit clocks below that. And in some sense, the matrix sizes are quite small. So this is also a big point here. On to Kepler. Kepler was the first graphics card that had a theoretical peak performance of teraflop. But here the problem is that the sizes of the matrices are actually too small. So let's continue. If we go actually with CUDA blasts, and I think this is still single precision, you actually do get 1 teraflop of performance, which is really good. Still for relatively small matrices. Okay, so then Pascal, you see with Pascal, you get 1.9 teraflop performance. And again, we have the single float performance, peak performance on Pascal is 9.3. So we're not there yet, but this is quite good. On small matrices again. Okay, if you run the CUDA blast, so you have 3 teraflop performance. Okay, so I do these experimental results to motivate that we're now very curious how come that we get such great performance. So we have seen the concepts, the memory hierarchies. Let's now see how the concept of tiling is applied in the codes. So the virtue of matrix multiplication is that it is still a relatively small, can be defined by a relatively small amount of instructions. Okay, so here is the code where we are working with single floats in a linear addressing space. The threads are organized in a two-dimensional fashion. So we have the block index, so we have a two-dimensional grid of blocks, and then within every block also the threads are then organized in a two-dimensional fashion. So we will get back to this example in the next lecture. So the main purpose of, we will look at this code not so much from the thread organization, but mainly from the memory organization. So we have the matrices A and B. There is data parallelism, so we are going to calculate where we are going to the size of the tiles in A, and then the step sizes, also the size of the tiles of B. Where do we begin, where do we end in these matrices? Every thread computes many inner products. So the inner products are accumulated in the register. So there is the C, big C sub, that is the local variable, the name of the local variable that will be stored inside a register. Okay, then we have the loop. So in a C loop, we can have multiple initializations and also multiple updates. So we are loading the tiles into shared memory. So using what is the block size. The block size was the templated. So perhaps I should scroll up. This is essentially C++ code. So the matrix multiplication is templated. So there is one parameter that is specified. And that parameter, the value of the parameter, is critical for the memory size. So there, in setting this, you take into account the available amount of shared memory. Your compiler will complain if you set this too high. So we have two tiles, one in A, one in B. We are loading the memory inside, so in two instructions. So this is data parallelism. Every thread has a first name and a last name, but this thread index.x and thread index.y. So there is the linear addressing space. So picture should have was in order to justify the precise instructions. Thread synchronization. So when these threads when the kernel is executed, you cannot be sure that the instructions are actually completed. So there might be one block of threads or one warp of threads that executes the instruction, but while another warp of threads is then still waiting to be scheduled for the instruction. So the synchronization means that all threads in the block, so if they are scheduled typically in multiples of 32, all threads actually have to wait. So this is this important synchronization directives that we are encountering here. There is the unrolling of loops, which is a general performance trick, also on CPUs that allows to take advantage of the pipelining. So that's what the pragma unroll does here. But the main point is again that the local variable, so in some sense it's now kind of counterintuitive. So this code is executed by an entire block of threads, and you tend to think about these tiles. So all the threads, probably I should have indicated as here. So we have the shared declaration here, but this gets loaded by the threads. So all the threads actually, each thread is going to load one element, is responsible for loading one element in the tile. Once the tile is filled up, and we can only do this when all threads are finished, so this is why the synchronization is needed, then we will make the inner products and write into that register. Again, it is one single variable here. You could think there's only one register, but no, there are as many registers as there are threads in the block, and actually as many registers in the entire grid. But in the grid, not every block is executed at the same time. So the number of registers that is active is equal to the number of threads that are currently executed in one block of threads. There is another important synchronization that happens. The synchronization is needed for the writing. So you see the index calculation that's happening here, which is stored in another register. So C, the little c, is stored in an integer register. Okay, this was a first pass through the kernel. I've not been able to explain everything, but I hope that the idea of the tiling became clear. Tiling is also critical when you think about shared memory, parallel linear algebra. And then we have the use of the registers, the shared memory, and the global memory. As an exercise, one should actually compute the compute to global memory access ratio of this block. So you can see that there are many more instructions, which is favorable for the programming model that we are applying here. In the next lecture, we will explain more about the use of the block index and how thread synchronization is used. Okay, we follow the textbook, hands-on parallel computing, which in turn is based on the CUDA C programming guide. The main purpose of the course is understanding, but the other purpose is that you will get some access to the literature. There is here the classical paper, Classical by Now, by Volkov and Demel, on dense linear algebra operations. The main exercise of this lecture, and this is essentially a paper and pencil exercise, is to compute the the compute to global memory access ratio. As this is a hands-on course, so you're very much welcome to take the very basic matrix multiplication code we started with and try to update this. So one would hope that you gradually also get more confident to write high performant accelerated code. Okay, so this is the next to last lecture in this first sequence on GPU acceleration. It got very technical, but I hope that the insights are also rewarding. And it gives somehow an understanding of what is involved in writing high performant code.